שלום לכולם. מצטער על האיחור, אנחנו עוד מעט נתחיל. רק רציתי לוודא שאתם שומעים אותי.
שומעים.
שומעים ורואים?
כן.
אוקיי. אז אנחנו מוכנים להתחיל. Okay, so let's switch to English and let's discuss the next subject, which is reflection symmetry. So, okay, so we all know what reflection is, and reflection is and if you have a line, and there is a point, let's call this point Z1, and we want to construct a reflection with respect to this line. So let's call this line X. So how do we reflect point Z1 with respect to the line X? It's very simple. We just draw another line which is a perpendicular to the line X. So it's 90 degrees. And then we measure this length, let's call this length A, and we draw precisely the same length on the other side, and then there'll be point Z2. And we can say that Z1 and Z2 are reflection of each other. So in other words, points Z1 and point Z2 are symmetric with respect to the line X. So this is what the symmetry with respect to line means. Okay, the line doesn't have to be X line, of course. We can draw another line, choose another point, I don't know, let's call it Z3. And then let's draw a line which will be perpendicular to this thing. So let's call this line S. And then there will be a point Z4 such that the pair of points Z3 and Z4 are symmetric with respect to line S. Okay, now, so this is the geometric construction. You give me a line, you give me a point, and I find you a mirror image of this point. Now, please note that if I draw a circle, let me draw a circle that passes through both points Z3 and Z4. Let me just draw a circle. So that's a circle. Of course, I can draw another circle as well. I can draw another circle that. So any circle that passes through points Z3 and Z4, this circle will intersect the line S, and when it intersects it, it does it orthogonally. So now let me define you something. So definition. Suppose S is a line or a circle. So what we're doing here, we're putting circles and lines on the same footing here. Then a pair of points, say Z1 and Z2 is called symmetric. Well, it's called symmetric. It's symmetric with respect to S if every line or circle that passes through these points intersects the line as orthogonally. So what I just did, I generalized the definition of two symmetric points with respect to a straight line such that it now includes the case of a circle. So with this definition at hand, I can not only tell whether the points are symmetric with respect to a straight line, the same definition now allows to define points that are symmetric with respect to a circle. So like I said, we put lines and circle on the same footing. And now, by now, it should not be surprising because we know that this is exactly what Möbius transformations, or as we call them alternatively, for partial fractional transformation do. So we know that Möbius transformation maps between lines and circles. So Möbius transformation, as a reminder, transformation. What it does, it maps lines and circles into lines and circles. Moreover, this transformation preserves the angle between curves. Yeah, so the angle between curves is preserved. So it means, what it means that if we have 2 points that are symmetric with respect to a straight line, and what it means that if I draw a line that connects these 2 points, it will cross the straight line S with 90 degrees. And now if I apply some Möbius transformation to this, so now I apply Möbius transformation T on this plane that maps all this into some other plane. So these points will be mapped. So this is the point Z1 and this is the point Z2. So this point will be mapped into TZ1 and another point will be mapped to another point, which is called TZ2. But what we know that these 2 lines will preserve the angle between these 2 lines will be preserved. So it was 90 degrees, it will remain 90 degrees. And if this was a straight line, if this curve was a straight line, let me make it choose another color. This was a straight line. So here it can be either straight line or it can be a circle. That can be a straight line or it can be a circle. And this line, it can either be a straight line or it can be another circle. And this then will be the point TZ1, and this is the point TZ2. but these two circles or lines must have 90 degrees at their crossing angle. Any questions so far? Okay, so if you understand all that, then let's formulate a theorem. Suppose S is a line or circle and suppose the point Z1 is a point and Z1 does not belong to S. So this point is not on the line S. Then there is a unique point Z2 such that the pair of points Z1 and Z2 is symmetric with respect to the line S. So how do we prove this theorem? It's very simple. Let me sketch you the idea of the proof. So suppose there is both the line S is a straight line, and there is a point Z1 which is not on this line. How can we make sure that there exists one and only one point which is a reflection of this? Well, essentially we go back to our intuition of elementary geometry, and we do precisely this construction. We draw a line that passes through point Z1 and is orthogonal to the line S. And then there's only one point on this line that has the same distance from the line S as the point Z1. So this would be the point Z2, and this is the only point which is symmetric with respect to line S. So this is elementary geometry. But now suppose that line S is not a straight line. Suppose it's a circle. So there's a circle S here, and there is a point Z1, I don't know, somewhere here. How can we construct a symmetric point with respect to the circle S? Okay, so what we do, we construct a Möbius transformation C of Z such that it sends this circle into a straight line. Sorry, that was not successful. Straight line, that's a better straight line. So T of S sends the circle into a straight line. And then this transformation will send point Z1 into some other point, T of Z1, which we call W1. But now on the W plane, so this would be Z plane, on the W plane, we have a point W1 and a straight line. And we know that with respect to straight line, we can find its symmetric partner. So this will be W2, which is symmetric with respect to line. And then, since Möbius transformations are reversible, we constructed an inverse transformation T-1, and apply to W2. And this sends point W2 back onto Z plane, and there will be some point C minus 1 of W2. And this point will be a symmetric point on a Z plane with respect to a circle.
אפשר לשאול שאלה? איך זה מוכיח אבל שזאת רק נקודה יחידה? כאילו אולי יש כמה טרנספורמציות שמעבירות לכמה קווים שונים ואז יש כמה נקודות כאלה?
אוקיי, מה שעשינו, אנחנו השתמשנו בהנחה שיש רק דרך אחת למפות את המעגל ב-Z plane, מעגל שביחס אליו אנחנו מחפשים את נקודת שיקוף, לקו ישר.
אוקיי, סבבה. תודה.
אוקיי, זה משהו שכנראה צריך להוכיח בנוסף.
כן, תודה.
אוקיי. So now what we're going to do now, let's play with this definition a little bit. So we formally defined it, but now let's explore the geometric meaning of reflection with respect to circle. And just to focus on something simple, let's focus on a unit circle. So let's discuss reflection with respect to unit circle. So the problem would be like this. We are given a unit circle, minus 1, 1, minus I. And now I'll give you a point somewhere, and you need to draw me a point which is a reflection with respect to unit circle. Okay, so to solve this problem, we obviously need to know how to map unit circle to the straight line. And we already kind of solved this problem because if you remember, we've learned before that there is a transformation Z minus I over Z plus I that maps between the real axis and the unit circle. So in a previous discussion, last time or one before last, we have seen that this transformation Z minus I divided by Z plus I maps the straight line into a unit circle. So the point minus 1 was being mapped to the point I. Point 1 is being mapped to the point minus I, and point 0 is being mapped to the point minus 1. So that was this transformation. So now what I'm going to do, let's do an opposite. Let's construct a transformation that maps unit circle onto a straight line. So this would be a transformation T of Z, which is in reverse of what I just wrote. And I claim that this transformation sends a unit circle onto a straight line, precisely in this order. So if I denote here points minus 1, 0, and 1, that the point minus I, will be sent to 1. The point I will be sent to minus 1. So if I go along this circle from point, and the point 1 will be sent to the infinity. So t of 1 is infinity, t of -1 is 0, t of I is -1, and t of -I is 1. So if I start with the point 1, then I'm being mapped to the infinity. If I go to the point I, I'm in the -1. If I go to the point -1, I'm at 0. So when as I go from I to -1, I cover this thing, and as I go from -1 to -I cover this thing. Okay. So now if you have a point Z1 somewhere here, it will be mapped to a point W1 somewhere there. And this W1 is just -I Z1 plus 1 divided by Z1 minus 1. So, okay, so here there is a point W1. And now if you want to make a reflection with respect to a straight line, which is a real axis, it's pretty straightforward. What is the reflection with respect to real axis? Of course, it's what happened to that? Okay. So what is the reflection with respect to real axis? Of course, I can draw a line, measure same distance, and draw a point, which will be a reflection of W1 with respect to real axis. What is the algebraic? What is algebraic a manipulation I need to perform in order to get this point W2? It has a very simple algebraic meaning.
צמוד.
Say it again.
צמוד.
Exactly. So point W2 is just a complex conjugation. Sorry, let me take it back. Point W2 is a complex conjugation of the point W1, which in this case will be I Z1 plus 1 Z1 minus 1. So this is the point W2 on this plane. And now I want to send it back. I want to send this point back to get a point somewhere on the Z plane. So I'm sending this point back somewhere there. It will be point Z2, and Z2 will be C minus 1 of the point W2. So I need to construct transformation C minus 1 of W for the transformation I just drew. And this transformation is, of course, the transformation we discussed at the beginning of this topic. So if I put there point W2, and now for W2, I substitute this expression. So this is my result for W2, and I plug it into this equation. So I get I Z1 plus 1 Z1 conjugate minus 1 minus I z1 plus 1, z1 minus 1 plus I. And now I simplify this expression, and I get that this is 1 over z1 conjugate. Now, what does it mean geometrically? So if I think about complex number z1 as its absolute value, let's call it R1, and a phase I theta 1, then this point will be 1 over R1 e in the power minus I theta 1, because it's a complex conjugate. So this will be the point 1 over R1 e in the power exponent of I theta 1. So what does it mean geometrically? It means that this point has the same phase, on the complex plane as the point. So this is the point Z2. So what we have computed is the point Z2. So we see that the point Z2 has the same phase as the point Z1. So if I draw a circle on a complex plane, that would be a unit circle. And I pick point Z1, I don't know, somewhere, will be a point Z1, and it has a phase theta, then its reflection will also have the same phase. So it means it will lie on this straight line that goes between the center of the unit circle and the point Z1. And now what is where on this line the point will lie? It will be somewhere here. So it will be distance at a distance R2 from the center, and R2 is just 1 over R1. So the further you take a point, the further you take the point from the center there, the closer to the origin you get its reflection. The closer to the boundary you take the point, the closer to the boundary you get the reflection. The point at infinity will be mapped onto the center of the circle. So
can I have some?
Yeah, sure.
How did we get the same phase? Isn't 1 over e to the theta just minus? What happened? So with
here it says 1 over z complex.
Because of the complex conjugate.
So complex conjugate changes the sign of the phase, and then it's 1 over, which takes it back. So it takes it back, and then we end up having the same phase. Okay.
Yeah, thank you.
So if I just want to focus on geometric meaning of this construction, I have a circle. I don't need to know about complex numbers at all. I have a circle placed at some point O, and then I'm giving a point P. It might be inside or outside of the circle. It will be some point P. So what do I do geometrically to find its reflection image? I draw a line from the center of the circle through the point P. And then, okay, so this is my point P. And then I think somewhere there, it will be another point, which will be a reflection of the point P. Let's call this point P prime. So they will lie on the same straight line. And I know that the distance OP, this is the distance between point O and P, times the distance between point O and point P prime is just 1. Okay, or in other words, OP is equal to 1 or OP prime. Now, we did this construction. For the unit circle, but of course, it's very simple to generalize this, to extend this construction for a circle of the radius r. Yeah, so if this is not a unit circle, if it's the circle of the radius r, then then what would be here will be the radius of the circle square, and this will be there. And this will be generalization of this construction for any circle. And this is purely geometric construction as you see, and this is actually known in geometry. It's called inversive geometry. So this reflection originally appears in inversive geometry, and inversive geometry is the geometric study of transformations of the Euclidean plane that maps are circles, all lines onto circles, all lines, and preserves angles. So we didn't study geometry, we studied complex analysis, and we focused on the conformal mappings. And what we discovered, what we discovered in this naturally is inversive geometry. And this is a very rich branch of mathematics, of geometry. So yeah. So if I'm trying to summarize this story, we are now given a circle. It does not have to be at the origin. Somewhere there's a circle of a radius r. And then we are given points that can be either inside or outside circle. Say there is a point here, then it will have a partner there, or there is another pair of points, say here, and it will have partner there. And the closer we come to the origin, the farther away will be the partner, and the closer we come to the boundary, the closer to the boundary will be a partner. So this is the meaning of inversion transformation with respect to circle. It's really popular transformation in geometry, and it has lots of application in all kinds of branches, including art and engineering. Okay. So now after we learned and understand a little bit conformal transformation, let's apply it to our favorite subject, to the subject of differential equations. And formally what we're gonna do, we're gonna focus on what is called Dirichlet problem for harmonic functions. Functions, I remind you that harmonic functions are functions that satisfy Laplace equation. These are harmonic function, and Dirichlet problem is a problem of solving differential equation. So it needs to solve differential equation, solving differential equation with a boundary condition. So if we have domain D, and this domain has a boundary delta D, that's the boundary of the domain. then we are given an equation and we are given a boundary condition on this boundary. So for the harmonic function, it means that we have equation dx squared plus dy squared equal to 0, and we know function u of x, y at the boundary of a domain. And domain can be any domain on the plane. So let us see how knowing complex analysis facilitates solving this kind of equation. Of course, you can solve this equation without knowing complex analysis, but let's try to connect it with a complex analysis and with conformal mappings. So a simple example. Find a harmonic function u of x and y. This function satisfies the Laplace equation. That has a boundary condition. The boundary condition u of x and y for y equals 0 is being theta function of minus x. So what it means that if there's a plane, x and y plane, then there is a real axis, which is y equal to 0. So on the real axis, there is a part of the real axis which are negative semi-axis here. And here this function u is equal to 1. And on the rest of the real axis here, u of x, y equals 0 is just 0. So very simple boundary. So the domain D in this case is, let's say, an upper half plane, and we know the boundary condition on the real axis. Let us solve this problem. Okay, so how are we gonna solve this problem? We're gonna employ the ideas of complex analysis. In particular, we know that real and imaginary part of any analytic function are necessarily harmonic functions. So if only we can now guess, quote unquote, an analytic function such that it's, I don't know, real or imaginary part will have the right values on the real axis, then the problem is solved. Can we guess a function, an analytic function that will be analytic in the upper half plane such that its, I say, imaginary part will be compatible with these boundary conditions? Any ideas? Try to guess. So we're looking for function, some function of the complex variable z. So we are defining complex variable z, which is x plus iy. And we want to find function f of z such that it's a real or imaginary part, doesn't matter. One of them takes jumps between 0 and 1, or jumps between two constants for positive and negative x. So what function has this property?
I mean, just a step function.
Yes, that's the step function of the real variable, but the step function theta of x, of course, does the job, but we need to have a function which is the function of z, such that it's an analytic function.
But on the real axis, we can just say that it's theta of z because y is equal to 0.
Yes, and if it's not, but we need, right, on the real axis it's just theta of z. So we need to find a function . Are you there? So we need to find a function that is defined not just on the real axis. That's the whole point. That's actually the central point of this construction. So now we need to find a function of the complex variable z such that it matches with the theta function on the real axis. And you know this function. So that's the whole point. You take the problem from being defined on the real axis. You take this boundary condition that you understood very well on the real axis as a function of x, and you want to understand them as a boundary condition for on the complex plane, for the complex variable z. So what will be the natural way to interpret function theta function of x as a function of the complex variable z, such that this function is analytic?
אם בחלק הממשי יש את הזווית תטא, או משהו כזה, אז כאילו על הציר, כאילו על החלק החיובי של ציר ה-X, הזווית היא 0, ועל החלק השלילי זה בדיוק פאי, אז יכול איכשהו להיות קשור.
בדיוק, זה לגמרי חשוב. אז אם יש לנו פונקציה ארגומנט, של z, זה בדיוק מה שזה עושה. כמו שנאמר פה, זה שווה ל-0 כאשר x חיובי, ושווה לפאי כאשר x שלילי, on the real axis. ומפה לעשות מדבר הזה, התטא פונקשן של מינוס x, זה בא בקלי קלות. עכשיו, הדבר היחיד שחסר, שפונקציה ארק, z, ארגומנט של z, זה לא פונקציה לפני עצמה, אבל היא מופיעה כחלק של פונקציה אנליטית מוכרת, שנקראת לן. אז אם אנחנו לוקחים לן של z, אז אנחנו יודעים שזה לן של absolute value של z, ועוד i ארגומנט של z. ולכן אם אנחנו ניקח את הלן של z נחלק את זה בפאי I, וניקח מכל הדבר הזה real part, אנחנו נקבל בדיוק את הארגומנט של z של k פאי, וזה בדיוק שווה לתת הפונקציה של מינוס x. ולכן, I'm teaching right now. אוקיי, אז יש לנו תטא של מינוס x, וזה בדיוק ה-boundary condition שאנחנו רצינו. לכן אם אנחנו בוחרים פונקציה לוגריתם של z, ומחלקים את זה בפאי I, וקוראים לזה פונקציה פאי של z, אז יש לפונקציה הזאת real part ו-imaginary part. By construction they must be harmonic function, ולכן הדבר הזה, u של x ו-y, on the complex plane, או u של z, זה real part של 1 over pi I logarithm z. So this function is necessarily harmonic, we know that, and we know it has the right boundary conditions of the Dirichlet problem, and therefore the problem is solved. Okay, did you follow this example? If anybody has a question about this example, because we're going to use this example for further investigations. Please ask now. Well, if everything is clear, let me now just build on this example and solve a very similar problem. So suppose there are 3 points, x1, x2, and then 3 ordered in this fashion. And then we want to find a harmonic function. U of x and y that satisfies the boundary conditions. And let me specify the boundary conditions. So again, at the same real axis, the boundary conditions are set on the real axis, and they are that the function is equal to C0 for x smaller than x1. It's equal to C1 on the x1 lesser than x2, equal to C2 for x2 lesser than x3, and equal to C3 for x greater than x3. So if I draw it on a, let me draw it here. So if I draw, this is the real axis. So there are points x1, x2, and x3. So at each of these intervals, the function u has different values. So here it will be C0, here will be C1, here will be C2, and there will be C3. So function jumps from C0 to C1 to C2 to C3. And there is a y-axis, that's an x-axis. And I want to find the function, I don't know, in the upper half plane. How do I solve this problem? And I based it on the previous problem where what we did, we took a point z, that was a z point. Then we draw a line and we call this angle theta. And we formulated the boundary condition in terms of this angle theta on the complex plane z. We said that here on the positive semi-axis, the angle theta was 0. On the negative semi-axis, the angle theta was pi. And that's what allowed us to find, to pose the boundary conditions on the real axis. So now how do I pose boundary conditions on the real axis when the function jumps? How do we do that? Please help me. It's based on the same idea, just taken one step further.
אולי אפשר למפות את זה למעגל, את התנאי שפה, ואז יהיה אפשר להסתכל כאילו כמה זוויות או משהו כזה?
אוקיי, בוא ניקח את חצי מהרעיון שלך, כי כמובן שאפשר למפות את זה למעגל, אבל אני רוצה כרגע להתמקד דווקא בקו ישר, כי כמובן שניתן לפתור את זה גם על המעגל, אבל בואו נסתכל על זוויות, על כמה זוויות, ופשוט נסרטט את הזוויות האלה. אוקיי, אז אני מנסה לשרטט זווית, אוקיי, זווית, בינתיים בסדר, זווית, ובואו נקרא לזוויות האלה תיטה 1, תיטה 2 ותיטה 3. זה זוויות בין נקודה Z והקווים שיוצאים מנקודות x2, x1 ו-x3 שבהם הפונקציה קופצת על השפה. אוקיי? אז איך אני יכול להגדיר את ה-boundary conditions על השפה? באמצעות זוויות תטא 1, תטא 2 ותטא 3. מאוד דומה למה שעשינו מקודם באמצעות זווית תטא. אני פשוט משתמש באותו רעיון ואני כותב C3 ועוד C2 מינוס C3 זווית תטא 3 חלקי פאי, ועוד C1 מינוס C2 זווית תטא 2 חלקי פאי, ועוד C0 מינוס C1 תטא 1 חלקי פאי, ותשימו לב מה קורה. אם אנחנו נגיד נמצאים בנקודה פה, הכי ימינה שאפשר, כל זוויות תטא הם אפסים, ולכן האיבר הראשון שורד והוא נותן C3. אם אנחנו נמצאים בנקודה ירוקה פה, אז זוויות תטא 1 ותטא 2 הם אפסים, אבל תטא 3 הוא פאי, ולכן מה ששורד זה C3 ועוד C2 מינוס C3, ולכן אני נשאר עם C2. עכשיו אם אני מגיע לנקודה הצהובה פה, אז T2 ו-T3 הם פאי ו-T1 הוא 0. אז לכן מה ששורד זה זה וזה, ויש לי C3 ועוד C2 מינוס C3, זה C2 מינוס C2 ועוד C1, אז C3 ועוד C1 מינוס C3, C1. ולכן מה ששורד C1. ואם אני הגעתי לנקודה הכי שמאלית, פה, אז כל הזוויות הם פיים, ואז יש לי C3 מינוס C3 ועוד C2, מינוס C2 ועוד C1, מינוס C1 ועוד C0, אז אני נשאר עם C0. ולכן מה שבניתי, יש לו בדיוק ה-boundary condition המתאים. ועכשיו איך אני הופך את הזוויות האלה לפונקציה אנליטית מקומפלקס אנליסיס. זה הצד האחרון בסיפור הזה. איך אני הופך, אם אני כותב עכשיו פונקציה U של Z, להיות, איך אני כותב פונקציה או יותר נכון, איך אני כותב פונקציה שהיא מייצרת לי את הזוויות האלה?
זה לא יהיה פשוט סכום של לנים?
בדיוק, איזה לנים יהיו פה בסיפור הזה? מה יהיו הארגומנטים של לנים?
אני לא יודעת להגיד.
אוקיי, זה נקודה סופר חשובה פה בכל הסיפור הזה. איזה לן ייתן לנו זווית תטא 3 של איזה ארגומנט? לן של Z, אם את זוכרת, ואת בוודאי זוכרת, לן של Z נתן, זה Z נתן את הזווית שיוצאת מראשית הצירים. אם יש לי זווית שיוצאת מאיזושהי נקודה אחרת, נגיד, זאת נקודה x1. לן של איזה ארגומנט אני צריך לקחת שהוא ימדוד לי את הזווית מהנקודה הזאת?
z מינוס x1.
בדיוק, z מינוס x1. זה פונקציה שסופרת את הזווית מנקודה x1. ולכן כדי לקבל את הקונסטרוקציה הזאת, אני פשוט חוזר על אותו תרגיל שעשינו מקודם, אבל פעם כותב u של x ו-y, זה real part של c3 ועוד c2 מינוס c3 חלקי i פאי, כפול לן של z מינוס x3, זה נותן תטא 3, ועוד c1 מינוס c2 חלקי i פאי, לן של z מינוס x2, זה נותן תטא 2, ועוד c2 מינוס c3, טעיתי פה, טעיתי, זה c0 מינוס c1, אז זה צריך להיות c0, טעיתי אצלי בנוט, c0 מינוס c1 חלקי i פאי, לוגריתם z מינוס x1. c0 מינוס c1. אוקיי? וזה יוצר את הקומבינציה של הזוויות המתאימה, וזאת פונקציה אנליטית עם תנאי שפה נכונים, ולכן ה-real part שלה הוא בהכרח פונקציה הרמונית. הבנו את התרגיל הזה? אוקיי, אם אנחנו הבנו את התרגיל הזה, עכשיו אנחנו מגיעים למעגל. כמובן שאנחנו יכולים לעשות את זה במעגל, כי במעגל גם כן לפתור משוואה דיפרנציאלית. זה לא מסובך מדי, אבל אני רוצה לשלב את הרעיון של הפתרון של פונקציה אנליטית ו-conformal mapping. אז עכשיו אנחנו מגיעים למעגל ופותרים בעיה הבאה. Example, find a harmonic function. U of x, y, say within a unit circle, that satisfies boundary conditions, and boundary conditions are u as a function of angle is equal to 1 for the angle that runs between minus pi over 2 and pi over 2. So if I want to draw this schematically, then I have a unit circle. And then on the unit circle, I have a part of this unit circle. That angles runs between minus pi over 2 and pi over 2. So on this purple line, this is where the function has a support u equal 1. And on the black line, it has a support 0. So this is my boundary conditions, and I want to find the function inside the unit circle. Okay, so how do we solve this problem? And the solution is just a combination of the exercises that we did before of the solving problem with the boundary condition on the real axis and the mapping that since, are we there? Okay, good. And the mapping that sends unit circle on the real axis. So let's do it in 2 steps. Step number 1, we know that there is a map W is equal to minus I z plus 1 z minus 1. This map is denoted as T of z. And what this map does, it sends the unit circle onto a straight line. So if I have unit circle here, I'll get a straight line, and moreover, this part of the unit circle, let me use a different color. This part of the unit circle, where the function has a finite support equal to 1, this part of the unit circle will be sent onto these parts. So this point minus 1, and there is point 1. So this is the bar function has a support u equal 1, and the black part of the unit circle is here. The function has a support 0. So now how we gonna solve this problem? We send it to the problem on the plane where the boundary conditions are on the straight line. We already know how to solve a problem with the boundary condition on the straight line. We find the solution on the W plane. So this is a Z plane, this is the W plane. We find the solution on the W plane, and then we send it back to the Z plane. So how do we solve the problem on the boundary plane? Oh, well, we know it by now. There is a point W here. We draw lines. We denote the angles. That would be the angle, I don't know, T1, and then will be angle θ2. And then we need to write a function which is just appropriate combination of angles, which will be just 1 plus θ2 over pi minus θ1 over pi. And then we translate this function into logarithm. And that would be the real part of 1 plus 1 over pi I logarithm of W plus 1. This is phase θ2 minus 1 over pi Y logarithm of W minus 1. And this yields phase θ1. So now we know the solution on the W plane very well. So what we need to do now, is map it back onto Z plane. So now we have this solution and we map it back using transfer. So if if T of Z was sending points from Z plane to the W plane, then there is inverse transformation T minus 1, which is also uniquely defined, will send us back to the Z plane. So I just plug it in and I say that this will be a real part of 1 plus 1 over pi I logarithm of minus I Z plus 1 Z minus 1 plus 1 minus 1 over pi I logarithm of minus I Z plus 1 over Z minus 1 minus 1. And I'm done. So I solved the differential equation with the given boundary conditions, but remember, I actually never solved differential equation in the usual way. I was not thinking about how I solve differential equation. I just constructed analytic function, and I knew that its real or imaginary parts are necessarily harmonic functions, and I only needed to match the function that has the right boundary conditions. Now, of course, for the problem like a circle, you don't need to do that. You can just solve Laplace equation in cylindrical coordinates. However, the big advantage of this method that if you're given a domain which is more complicated than a circle, then we know that at least theoretically, there is always a transformation that maps this domain on a much simpler domain, say onto a unit circle. This is just a Riemann mapping theorem. Remember, any simple connected domain, which is not the entire complex plane, can be mapped onto a unit circle. And therefore, if we are given a problem like find a spectrum of oscillations that satisfy the Laplace equation, this is the typical problem in elasticity, on some manifold that is very complicated, has a complicated boundary, it's a bridge, it's a drum, some other musical instrument. And then it's very hard to solve differential equation on this complex boundary condition. But if you know how to map this manifold onto a simpler manifold, that the problem of solving differential equation essentially boils down to the problem of mapping this manifold onto a simple manifold. Which is a unit circle, or can be mapped from there, as we know, onto the real axis and semiplane. That's the old story that we learned today. So therefore, if we are dealing with two-dimensional Laplace equations, solving them for complicated boundary conditions is equivalent to a mapping of these complicated boundary conditions onto a simple domain. And this is heavily used in two-dimensional ideal hydrodynamics, in elasticity problems, in electricity. So that's where ideas of complex analysis are being very useful for physicists. One of many domains where complex analysis helps physicists. Okay, people, I think there's time left for questions here, because we more or less finished this topic of conformal mapping and the connection to harmonic functions. So, and my plan for the last part of the course is to focus on integral transforms, in particular on Fourier transform, Laplace transform, and if time permits, Hilbert transform. But we'll see how fast we manage. But more or less, this ideologically, I covered this point. So please ask any questions that are left unsolved.
Why are the symmetric pairs important. We found a way to find these symmetric pairs given a point. Why are they important?
Well, for one thing, I wanted to connect complex analysis with geometry. Now, in geometry, in inversive geometry, there are many very beautiful construction of very famous curves that are important in arts and engineers and engineering, and they were known. Some of them were known for ancient Greeks, and some of them were discovered recently. And so there are beautiful mathematical curves that emerges in geometry, and they naturally appear in the complex of complex analysis. Now, another thing that we will be interested in the reflections, then when we will be solving boundary problems. So sometimes it's very useful when you continue functions analytically to think how you can continue a function with respect to a boundary. And then the idea of what points are symmetric with respect to this boundary is also important.
Also, more recently, you said that if the boundary conditions are not very easy to express in a certain plane, we can just make a transformation. But is it and find that will transform it into a simpler boundary condition? But
Right.
Does such a transformation always exist? Like the boundary condition can be as complex as can be.
Define exist, because I think you mean something which is not what mathematicians mean. So in mathematical sense, such transformation always exists because there is a Riemann's mapping theorem that tells you precisely that any domain can be mapped onto any other simple connected domain. Any simple connected domain can be mapped to any other simple connected domain, in particular to unit circle or upper half plane. The question is whether it's easy or not to construct such transformation explicitly. That's a different question, and in some cases these transformations are extremely difficult to construct, but in some cases they are doable. And like my daughter says, I'm talking from the experience. I have one problem that I solved precisely by mapping a very ugly or very unusual boundary, very unusually posed boundary condition onto the boundary conditions posed on the unit circle. It took me some time to construct this transformation. That was not simple, but eventually I managed and it worked. So it's just a tool in a toolbox that may come helpful. Obviously, nobody guarantees that it will always be easy.
How do you find such transformations? Are you just guessing and then readjusting accordingly? Like,
yes, I don't think there is an algorithm. I don't think there is an algorithm that you can construct. It's essentially guesswork combined with experience. At least I'm not aware of any constructive algorithm how you can program think you're given a domain, how you can construct an approach that will generate a mapping. You can call it guessing or thinking depending on your attitude, but at least I'm not aware of any algorithm that does it. Okay, but that's a very beautiful mathematical construction in my mind. Okay, people. So if we have no more questions, so let's stop here, and see you next week with aiming at integral transformations. By the way, did you have a chance to learn Fourier transform and Laplace transforms in previously? Because sometimes people mention it before.
I'm not entirely sure.
So the question is, do you know the main properties of Laplace transform and Fourier transform and how you use them to solve differential equations? Because depending on that, I'll go either slow or fast. So if you know how to use Fourier transform, I'll just put it in the bigger context of complex analysis. But if this is the first time you ever hear about Fourier and Laplace transform, then I'll go much slower, and then I'll probably skip Hilbert transform. So it's a simple question. Have or haven't you learned Fourier transform? Or
סטודנט תמיד יכחיש ידע קודם, אבל אני לא יודע. אני לא זוכר, כי אולי, אני לא יודע אם דיברנו על זה בקונטקסט של משוואות דיפרנציאליות, כאילו...
Okay, that's the main context of this transform. So, okay, so let me just focus. So even Fourier transform, which is the most common one, it's not something that you know very well. Is this statement correct? It's young.
אני מנסה לחשוב, כאילו, מה עשינו?
It's something that you either want or don't like. The more it's your goal is to learn, and I adjust myself to give you as much as I can. So if you know it, there is no point wasting your time on that. If you don't know it, there are lots of sense, of course, to focus on this. So that depends on whether you know it sufficiently well or you don't. Because the point, like I said, is to teach you something that you don't know. But if Fourier transform is something that you don't know, then I'll focus on the Fourier transform. If you know Fourier transform, I'll teach Laplace, and if you know that, I'll teach Hilbert. You need to tell me.
טרנספורמציה פוריה, אתה מתכוון לפתור את המשוואה במישור פוריה ואז לעשות טרנספורמציה חזרה? נגענו על זה בממפיס 3, זכור לי. אני אשמח לרפרש.
Okay, בסדר. So we'll focus on Fourier and Laplace, and we'll probably leave Hilbert out of this story because it's less frequent. Okay, people, so here we stop, and goodbye for now.